Hello everyone, welcome to our new video. We continue with linear algebra and discuss the determinant of a matrix. So first we have some properties of the determinant of a matrix. Suppose we have a n by n matrix. If matrix B is obtained by multiplying a row or column of a matrix by A by a scalar k, then we have the following property that the determinant of B equals to k, this is the scalar, times the determinant of A. For example, suppose we have this matrix given 3, 15, minus 17, and so on. And we can notice that this column here actually is multiplied, each element in this column is multiplied by 3. Okay, so we can factor out these scalar multiplication out of this column, okay, and write down 5, 3, and minus 4. We factored out this 3 out of the matrix A. So this is equal, basically, 3 times the determinant of this matrix A in this example, and this becomes our matrix B. The second property, again, we have the n by n matrix A. If B is obtained by swapping 2 rows or columns of matrix A, then we have the determinant of A equals to minus times the determinant of B. Okay, so if we swap 2 columns or 2 rows of a matrix, then the determinant will be multiplied with a minus sign. This is what we are saying. The third property, if 2 rows columns of a matrix is equal, then determinant of this matrix equals to 0. So we can see a direct example. Suppose I have 1, 2, 3 as the first row, and then the third row is also the same. In that case, the determinant of this matrix equals to 0. Another example, let's say our matrix A is given, and you can notice that this time 2 columns are the same. All the elements are the same, so these 2 columns are identical. That implies basically the determinant of this matrix will be equal to 0. Fourth property, if we have a 0 row or column in a matrix A, then again the determinant equals to 0. So if we have a row or column of zeros completely, like this example, the second row is contains all the elements equal to 0 in the second row, then we can directly say this determinant equals to 0. Suppose we have matrix A, n by n, and then we denote the elements of this matrix as A, I, J. Then first, if A is a 1 by 1 scalar, then the determinant of this scalar, which can also be written as a 1 by 1 matrix, equals to the scalar itself. So the determinant of, for example, minus 3 equals to minus 3. Okay, it is equal to itself because it's just a scalar number. Second, now let's consider a 2 by 2 matrix. The determinant of a 2 by 2 matrix is given by we cross multiply A11 times A22 and then subtract the other cross term A1 to A21. So the 2 by 2 matrix determinant can be calculated using this formula. If we have a 3 by 3 matrix, then how do we calculate the determinant? If we have a 3 by 3 matrix, then we are going to use one of the rows or columns, and we take it as the pivot row or column, and then write down the determinant of the submatrices, multiplying these determinants with the elements of this fixed row. Okay, so if I fix, for example, the first row for this determinant operation, then I'm going to use the first element, and then if I use this element, okay, the remaining submatrix will come from here, A2 to 2, 3, 3, 2, and 3, 3. As you see, this is the first submatrix because we use A1, 1. Remaining terms, basically meaning that I pick the submatrix here. So I cross this guy and just consider the remaining submatrix. And then I move on to the second element, A1, 2. This time I will cross this guy and consider A2, 1, A3, 1, and A2, 3, and A3, 3. As you see, it is given here. Okay, so I am taking this element second, and then the remaining submatrix is here. So you take the determinant of this submatrix, and then the third element, we move on here, we fix these terms, and then consider the remaining submatrix here, and that gives us the term, the submatrix times A1, 3. And pay attention that there are alternating signs for the coefficients A1, 1. Here we have a minus and then plus again. So basically you can consider minus 1 to the power 1 plus 1, that's equal to 1 here. This is 1 plus 2, that is 1 minus 1 over 3, so it is a minus, so it's a minus sign here. Okay, so we have these alternating signs, and then this is minus 1 to the power 4, 1 plus 3, that's equal to 4, which is equal to, again, 1. So we have a positive coefficient in front of A1, 3. So this is the alternating sign. We need to multiply each of these elements with minus 1 to the power of the index I and j summed together. That goes to the power of this minus 1. So it determines whether it is plus or minus 1 according to the index. Here's an example. Suppose we are given this matrix A, and the minor, we call this minor M23. That means this is the determinant of, when we say second row, third column, second row, third column. So the minor that is denoted by M here, M23, equals to the determinant of 1, 2, y, and 7. And this is given as 5. So you can use this given information to find the value of y first, and then use the second information to calculate the value of the second variable x. And once we find x and y, we are done. And as you see, we call this submatrix, the determinant of this submatrix, as the minor, and this row and column indicates the exact elements of this minor. So as we know, from a 2 by 2 matrix, the determinant of this guy is 7 times 1 minus 2 times y. Okay, so 7 minus 2 times y equals to 5 from this equation. And that means y equals to 1, okay, from this equation. So once you solve for y, then you can go ahead and write down the determinant of a and solve this equation for x. We can solve it for x. And notice that we can fix this column as our pivot in the calculation of the determinant. So first, we can write down, as you see, we use this column. So I have 1 times, the remaining minor is here. That's the first one. And then I use the second element of the third column here, x, and we have a minus sign, don't forget, times the remaining is 1217 here. And then the third element here is 0, so 0 times the determinant is 0, so we don't need to write it. I can just write 0. And as you see, this is 7 minus 2, that is giving us minus 5 times x. This is 21 minus 6 minus 5 times x. This must be equal to 30. And we can solve the value of x from this equation. If we have triangular matrix, the determinant now is going to be given by the multiplication of the elements on the diagonal. Okay, so if we have a triangular, upper triangular or lower triangular, doesn't matter. As long as we obtain a triangular matrix, the determinant is given by the multiplication of these terms on the diagonal. So for this example, 3 times minus 2 times 5 times 1 minus 30 is the determinant of this expression. Another example. Now, our original matrix might not be in the triangular matrix form, but we can convert it into a triangular form by doing some row operations. Okay, so by applying the row operations, for example, we can add the first row to the second row. That gives 0, 0, 8. Okay, or we can, for example, multiply the first row by minus 2 and then add to the last row, and this will become 0, 0 again here, and then 10 minus 6, we get 4. Now, as you see, this is now upper triangular matrix. The lower terms below the diagonal are all 0. So the determinant of this equals to the multiplication of the diagonal elements. 2 times 4 times 0 equals to 0. Another example, and before that we have the also property that if we have n by n square matrix, the determinant of the transpose equals to the determinant of the original A. And this is, of course, this property is not too difficult to verify. If we are given matrix A, then the determinant of this matrix is 4 times 1 plus 6, so this is equal to 10. Okay, this is 10. And you can easily verify and take the transpose and see that the determinant of the transpose is also the same. They are equal. Okay, another example. Suppose we are trying to find the determinant of this matrix here. 1, 1, 1, A, B, C, A square, B square, and C square. Now, we can simplify this by doing, again, some row operations. For example, this starts with 1. I can multiply this with a minus sign and then add to the second equation. For example, this gives us 1 minus 1, 0, b minus a, b square minus a square. Similarly, you can do the same operation with the third row, minus 1 and add it to the third row. This becomes 0, c minus a, c square minus e square. Now, we can factor out this b minus a that is common in these two terms, right? So instead of this, we can write as 0, 1, because b minus a, this is equal to actually b minus a times b plus a, right? So we can factor out this b minus a as a common term, because all these, and also 0, you can rewrite 0 as 0 times b minus a, doesn't matter, right? So actually this is still 0. That means I can take this b minus a that is existing in all the elements in this row, take it out, and then write this as 0, 1, b plus a. Similarly, factor out the c minus a common here, and you can, this is 1 here. Okay, this is 1. So we have c minus a, 0, 1, c plus a, just like the second row. And then you can multiply the second row with minus 1 and then add to the third row here, okay, after multiplying with the minus 1. So this term becomes also 0, and then you have c plus a minus b minus a, so this becomes c minus b here, okay. And we end up again with the triangular form we want. So the determinant becomes 1 times 1 times c minus b, but we already factored out these two terms. Okay, so the determinant of this expression equals to the multiplication of these three terms. Okay, example 5. So again, we are given, we are trying to calculate the determinant of a matrix A, but we still know that we can do some row or column operations to simplify this expression as much as possible. And once we are satisfied with the simplification, we can go ahead and calculate the determinant. By the way, this is also okay to directly evaluate this determinant without doing any row or column operations. That's okay. We will still get the same result, but we prefer to simplify that because doing this directly will be cumbersome. It will involve more calculations, and we can perhaps make a mistake more easily. So it is better, if possible, to simplify the expression by doing some row or column operations and then calculate the determinant for this problem. So, for example, we can multiply the third column by 4. We can multiply this by 4 and then add that, because as you see this is 1. So if I multiply the third row by 4 and add it to the first one, this term becomes 0. And remember, if I get these zeros, my calculation will be more simple. So you can multiply this by 4 and add to the first row. This becomes 14, 37, and 0. And similarly, you can multiply the last row by minus 2, and again, this time add to the second row because I want to make this 0. So I multiply this with minus 2 and add to 2, I get 0. Minus 20 and then plus 4, I get minus 16. Minus 6, minus 1, I get minus 7. The third row remains the same. Now I can use this column to calculate the determinant, but these two terms are 0, so they are automatically 0. I don't need to evaluate. And the last term, I cross these and consider the submatrix here. This is the submatrix times the coefficient equals to 1 here. And you can multiply these cross terms and then minus 37 times minus 7. This gives us 35 as the result of this calculation. Okay, upper triangular matrix. The definition is quite simple. You can see that if the upper terms above the diagonal are non-zero and below the diagonal terms are 0, we call this as the upper triangular matrix. And in a lower triangular matrix, the terms below the diagonal are non-zero, but all the terms above the diagonal, they are equal to 0. Here is another question, example. Suppose if the determinant of A, we are trying to calculate the determinant of this term, then what will be the determinant of B? Okay, in terms of the determinant of A, can we express this in terms of the determinant of A? And actually we can do that because we can actually do the row operation here. We can multiply the first column by minus k and add to the third column. Okay, this is the third column. So if I multiply the first column by minus k and add it to the last one, I'm going to obtain the original determinant of matrix A. And this is just equals to the determinant of A. Okay. So basically, since we are able to show by doing some column operation, we can get back the original problem, then these two are equivalent. Therefore, determinant of B is also equal to the determinant of A. Another interesting example. Suppose we have the unknown variable x, but this matrix, we have the determinant of this matrix, and the elements of this matrix are all in terms of the unknown coefficient x. All of them are unknown x. So how can we simplify this and calculate the determinant easily for this example? So we can reduce this problem by first notice that all of these terms include x. So we can factor out the x out of the determinant as a scalar. This is a scalar. Okay, so we have these terms now here. And we can notice that if we, for example, if we multiply the first column by minus 1, I multiply the first row with minus 1 and then add to the second row, I'm going to get this 0. This will become 0 and this will become minus x. So this is the new second row. Do the same operation with the third row and add it to the last row. This becomes 0 minus x, and 0. And then you can do one more round or simplification. You can notice that take out the x. We can take out the x. Sorry, we actually, let me go back like this. Actually, we are taking out this x in the second row, and then take out another minus x here. So minus x times x, it becomes x cubed, and the term here becomes 0, 0, 1, 0, 1, 0. And the last, remember, we can do a swap, interchange the second row with the third one, but we should not forget a minus sign comes out of this swap, interchange. So it becomes a upper triangular matrix, and the diagonal elements are 1 times 1 times 1 times this factored out coefficient. So we get the result for this example as minus x cubed. That's the determinant of this, matrix in terms of x. Another example, suppose we have again a determinant calculation and we want to simplify this. Our expression is given in terms of x, y, z unknown variables. So how can we simplify this and calculate the determinant of this problem? Okay, actually, again, we can think about some row or column operation to simplify this expression. And one thing we can notice is if I add the second column to the first one, that will make the first column, the elements becomes all the same. Okay? This is good news because if I get this, I can factor out the common term out as x plus y plus z, and this column becomes just 1, 1, 1. Now, we can think about now doing some row operations potentially, right? Because I can see that this one and this one I can cancel out by multiplying the first row by minus 1 and then adding to the second one. This 1 cancels and it becomes 0. This z plus x minus y minus z gives us x minus y. And this one, z squared plus x squared minus y squared minus z squared, cancels out these z squares. So I get x squared minus y squared. So this is x squared minus y squared. That is here. Okay, it is here. And then what about the third row? Similarly, multiply the first row with minus 1 and then add to the third row, and you get this 0, x minus z, x squared minus z squared. Now, one more step to go. Notice that before we move to next page here, you can notice that this is x minus y, x squared minus y squared. So it has this x minus y as a common term. So you can factor out x minus 1. So this becomes 1, and this other term becomes x plus y. If I factor out x minus y. So we factor out x minus y, as you see, and rewrite this second row as 0, 1, x plus y. And similarly factor out x minus z from the third row. So you get 0, 1, x plus z. X plus z, yes. And then one more step, multiply the second row with a minus 1 and then add to the third row. So I get rid of this 1. It becomes 0. x plus z minus x minus y, it gives me z minus y. Finally, we get our upper triangular matrix here. Okay, so the determinant is the multiplication of these diagonal terms times the coefficients that we factored out. So the result, these are the coefficients that we factored out, and then times there is a z minus y here. That is, the fourth element. So that's the result of this determinant calculation. So let's stop here with these examples, and in the next video we will continue from here. Thank you.